Welcome to this lecture number 30 of the course Computational Hydraulics. We are in module 2 numerical methods, and this is unit number 26 algebraic equation Newton-Raphson method. Learning objective: at the end of this particular unit, students will be able to apply Newton-Raphson method for iterative solution of nonlinear system of equations. Nonlinear equations, we have seen that if we have A phi equals to R kind of structure, then we can solve it using a linear direct or iterative approach, but in this case the requirement is that A should be with constant coefficients, but if this matrix A or its coefficients are functions of phi, then the situation will be different. So, in this case we can write the final form like this, where we have A11 is a function of phi, A11, A(n1), A(nn) is function of phi. Now, you may get this kind of structure during your discretization process. Now, how to solve this kind of problem? In lecture number 24, I have talked about two approaches. One is based on Taylor series, another one is based on optimization method. So, Newton-Raphson approach is necessarily based on Taylor series expansion approach. Now, in this case we can write again the full matrix form, and we can transfer this right hand side vector on the left hand side. This is left hand side portion and this is right hand side portion. I can just transfer it with a negative sign. Now, if I write that form with this f1, f2, f3 up to fn, remember that in this case we are representing each row with different nonlinear functions. F1 means this represents the first row, F2 it is a second row, F3 third row, like that, Fn is nth row. In compact form or with phi vector, I can write this as f phi. This is equal to 0, this is again vector. Obviously, individual terms will be 0 in this case. So, how to solve this particular problem? In final form, we can write this as f is again vector, phi is vector 0, this is again in vector form, this will be column vector or it is 0 values. So, we have to solve this nonlinear system of equations, and phi, this vector, this is represented in terms of column vector. I have used transpose. Similarly, f is also column vector like this one. Now, let us see how to use our Taylor series expansion of ith function. let us say f I is any arbitrary function. So, to represent that, if we have f phi plus del phi, phi del phi both are vectors. Now, in this case, if we give increment del phi 1 to phi 1 and del phi n to phi n, we can write the equation or this expression in terms of f I phi. F I phi is necessarily phi 1, phi 2 up to phi n. Now, in this case, if we expand it up to first order, we will get first order derivatives, and higher order, although terms will be there. So, in this case, we are taking up to first order starting from a function value, and we are neglecting, that is why we are using this approximate sign here. So, j starting from 1 to n to consider all the variables. Now, in this case, combining n function expansions, let us say that we have used it for ith function. Let us write it for first one, nth one, and in between for all the functions. If we write, we can approximate it with f 1, this is corresponding to this vector or function vector at phi, plus this is represented, this f 1 is represented, or this is differentiated with respect to all the variables starting from phi 1 to phi n, and we can multiply this column vector del phi 1 to del phi n with this one. So, this is a matrix representation of our Taylor series. Now, from this one we can get some interesting results. Obviously, in this case we have 1 to n. So, n cross n is the size of this Jacobian matrix. This is called as Jacobian matrix containing the first order derivatives of the functions with respect to the variables. Now, if we utilize this for our calculation, in the next step we can compactly write it in vector form. So, left hand side we have represented with vector with incremental variable value and a vector with phi calculated at that point. This is the Jacobian matrix, and again this is the column vector for increment, whatever we have considered in our previous slide. Now, at this point we can say that this particular J is the Jacobian matrix which is of the size n cross n. So, in this case our assumption is that we have n number of equations and we have n variables available. Okay. For n variables we have n number of equation available for us. Now, assuming that when we are giving increment to this phi, this will lead us to the solution of the system. So, we can assume that f phi plus del phi, this is equals to 0. Now, this is nothing but our previous equation. We have used 0 in place of f phi plus del phi. Now, in this case we can write it like this. So, this is j phi del phi equals to minus f phi. Interestingly, this is linear in nature. Why? Because Jacobian matrix that we are calculating, that is evaluated at the point phi. So, J is evaluated at point phi and its size is n cross n. So, we can say that it is equivalent to our original system, which is Ax or A phi equals to R, where J is the coefficient matrix and in place of phi we are writing this del phi. So, on the right hand side in place of R we are writing this minus f. That means function values evaluated at this phi point. Now, if we write the next step, this is nothing but we can invert this j and we can get the increment value for a particular point to get the ultimate solution. Now, for a particular point phi, if we apply this del phi increment, we should get the solution. So, we can apply this increment. So, if we apply this increment and we can write it in iterative form, let us say that we are starting from phi 0 point, okay, phi 0 point, and for pth or first one, that means at first iteration we need to calculate this del phi 1. So, if p equals to 1, so obviously this J matrix should be evaluated at phi naught. At first iteration we should take inverse this f phi 0. That means we can start from our guess value like the iterative technique that we have utilized for constant coefficient case. Now, we can get information about this del phi vector at pth iteration, where p equals to 1. We are starting from this guess value which is phi naught. Now, in this is valid for this particular step is valid for p greater than equals to 1. That means, starting from 1 we can start the iteration and we can add the increment with our original or starting point. So, explicitly we can write that this phi p or updated value equals to my old value and plus del phi p. Now, del phi p is again minus j inverse f phi. So, we are directly adding this with the old value. You can compare this step with our iterative technique used for linear equations. This is similar. We are adding or updating the value at a particular point. So, in this case this iteration starts with the guess value, which is phi 1 0, phi 2 0, phi n minus 1 0, phi n 0. Now, in matrix form essentially we are doing this, and this part is calculated at present time level present information level. So, present information level means that whatever value is available, we are calculating these derivatives or these function values with that information. That means, your constant coefficient thing, this is necessarily A inverse, and right hand side this is R and one negative sign is there. We can utilize this, or we can directly solve this A del phi equals to minus R kind of thing. So, where if we provide this minus R, where R vector is your F vector. So, we can utilize our linear either direct or iterative approach to get the solution or this del phi vector. So, we can utilize maybe LU decomposition in this case to get the solution. Now, residual error, like our iterative technique, we need to see residual error. This epsilon at pth iteration, again this is the increment. So, obviously, this increment should be checked. Now, what we can do, we can calculate root mean square error, and this root mean square error should be less than equal to some specified root mean square error level. So, this is the stopping criteria for this Newton-Raphson method. Now, let us consider one example. Now, example is that we can multiply this phi, these particular matrix, which is A matrix. This is with variable coefficients, this is not with constant coefficients, because phi 1, phi 2, phi 3, these are included in the coefficient matrix. Now, if we simplify this, we can write it in terms of f 1, f 2, f 3, f 4, f 5. Now, the solution you already know for this system is 1, 2, 3, 4, 5. Now, let us see how to solve this problem using Newton-Raphson approach with our Scilab programming. Now, this part is clear because initially we start the program with CLC, that means clear the screen, and console, clear the console. Then clear means we are clearing all the values that are stored in Scilab from our previous operation. Now, in this case I am utilizing LU decomposition. Whatever LU decomposition code we have written using Scilab, I will be directly utilizing that for this particular step. Now, starting from this one, we can say that up to this we have LU decomposition. Now, this is forward substitution, then backward substitution, and this is the end function. So, final we will be getting the phi value like our original problem, which is linear in nature, a phi equals to r. Now, let us write other vectors or matrices for a Newton-Raphson method. So, for Newton-Raphson method you need function value. So, for function value I have included one function which is fv. Fb is the function, this will give me function value. So, fun phi. So, if you give input phi, so this will give me the function value, and this is end function. And another thing is required, that is Jacobian value or JV. This is Jacobian matrix, we are giving input phi. So, we should get Jacobian matrix for this one. Now, if we complete this function value and Jacobian matrix, then we can start our original algorithm for Newton-Raphson. Now, how to write that algorithm? So, we can start from simple count equals to 0. Count means number of iterations, iteration counter in this case, and RMSE equals to 1 to enter into this while loop. So, phi o, this is Newton Rn, okay, Newton Raphson method. So, Newton Rn, phi o is the guess value, n is the number of variables, EPS max, this is the limit for RMSE. Now, what is the output? Output is count, that means number of iterations required, RMSE, root mean square error, and phi, that means after iteration whatever value we are getting as solution. Now, in this case let us start the while loop, RMSE greater than EPS max. Obviously, if we write RMSE equals to 1, that is greater than EPS max, and after entering into the loop I am writing this RMSE equals to 0, because I need to calculate this RMSE within this calculation or while loop. Now, we can first calculate this our Jacobian matrix and function value, Jacobian matrix and function value. So, if we write this, so d phi, what is this d phi? D phi is nothing but d phi in this case. So, first we have calculated Jacobian matrix, then we have calculated function value or FV, JV, FV, and this is our d phi. Now, this is matrix, this is column vector, this is column vector. Essentially, JV is with constant coefficient for a particular value of phi, and FV is again a constant value, and del phi or d phi is your variable vector. So, in this case if you utilize LU decomposition with a negative sign to minus r, because this is required, we need to place minus sign before r to get the solution of del phi, because this is the general structure. General structure was a phi equals to r, but if you want to use LU decomposition to solve this one, that is JV into del phi minus FV, we can transfer this information. that A and R matrix we can directly transfer to LU decomposition code to get the solution. So, with this we can add del phi I, that means ith update, and similarly we can calculate RMSE or by adding the del phi square values, and after this update we can store this old value in place of old value the new value, and we can again start the iteration thing. At the same time we are also calculating RMSE. RMSE equals to square root divide RMSE divided by n, because we have added all the values, divided by n, n is the number of variables, and count should be count equals to count plus 1. So, this is you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, 15 lines are required to write this Newton-Raphson algorithm. Now, we can solve it easily using Newton-Raphson. Another important thing is that initial guess. For linear case it is much easier to get the solution with our arbitrary values, but it is difficult for nonlinear case. So, let us examine that. We have two situations, let us say phi O1 where all values we are starting from 1, phi O2 where we are starting all values from 0, phi O3 this is arbitrary, arbitrary values, one value is 10, another one is 1, 100, 6, 11, anything. So, with these three values we will try to examine what is the solution. In this case we have utilized EPS max is 1 into 10 to the power minus 6 and n equals to 5, because we have 5 number of variables, and so we can call this Newton-Raphson method with values. Let us start with phi 1, phi O1, that means first guess, which is 1 1 1 1, that means all values are 1, and finally we are calculating this FV or FUN, that means function value. That means if we calculate function value at solution, it should be close to 0. So, let us try this. So, we can select this and we can select this and we can run this. Okay. If we run this process, then easily we can see that we are exactly getting our solution phi equals to 1 2 3 4 5, that is the solution, and RMSE we are getting this point 1 2 3 4 5 6 6 not 2, and with counter 9, that means within 9 iterations we are getting this solution, and finally whatever function value is there, that is minus 10 to the power minus 4, 10 to the minus 13, minus 14, minus 15, and this is very near to 0. So, we can say that our solution that is almost correct in this case, but let us see what is there if we change the initial guess. Let us say that all initial guess values are 0 or all variable values are 0 or phi 2, phi O2. So, in this case if you evaluate it, we are getting nan. Why we are getting nan? Because we are unable to calculate the Jacobian matrix properly. All entries in Jacobian matrix is 0. So, in this case it is difficult to get the solution, or it is impossible to get the solution with this guess. Now, if we use arbitrary value for this 3.503, then again we are getting the solution, solution 1, 2, 3, 4, 5, and RMSE also less. Count, this is important, because in previous case when we started the solution with 1, 1, 1 value, that means for first variable we have provided exact value, and for others there is less deviation in the variable values. So, in this particular case we are using this 503, that means 10, 1, 100, 6, 11, these arbitrary values are there. Obviously, you need more iteration to get convergence. So, in this case with 15 iterations we are getting the solution. Again our function values are very close to 0. I think this is clear that depending on the initial or guess value our solution thing will change. So, let us examine it from our Jacobian matrix. If we see the Jacobian matrix, almost all diagonal terms that will be 0 if we provide this 0 value as initial value for the solution process. So, with this we are finishing this numerical method this module, and from next module onwards we will be discussing the specific discretization for our computational hydraulics problems, and we will try to solve those problems using this Scilab codes. Thank you.